completely get rid of Fermi resonance in a molecule so that you have spectra that are more simplified and therefore easier to analyze. Of course, after you have analyzed that, you understood everything, you come back to the original molecule and then try to unravel the complexity that that molecule has in the first place. What I will do next, as I said, is to teach you something about Raman Spectroscopy, which is sort of removed from what is there in Banwell. It is really something that you will probably learn in greater detail later. But as I said, Raman Spectroscopy actually got a new lease of life when lasers came. Without lasers, Raman Spectroscopy would have been dead a long time ago. Raman is dead a long time ago. So, but once you had lasers, what is the problem with Raman? Raman spectroscopy it's a very weak process. It's a scattering process. It's not extremely strong. And to be able to see, particularly if you're looking at anti-strokes, you are sunk. It's already weak. And then you have an even weaker process going on. So we said that if you had lasers to operate with, and the lasers came about in 1961, the first laser was built by Ted Lehman, which is a Ruby laser. Immediately you had extremely powerful light sources. And once you had powerful light sources, the first thing that people did was just go back and do Raman with these powerful sources. And they found that not only were you able to do Raman spectroscopy much more efficiently, because you could do so many things. You didn't have to worry about using 300, 400 nanometer light. Scattering is pretty weak at 700 nanometers. But the power that I have in my light source is so enormous, I can still get good Raman scattering using 700 nanometer. Suppress fluorescence. And therefore the experiment suddenly became extremely powerful. And it became extremely powerful for many applications in chemistry, many applications in biology, material science, physics, and so on. And today you find that there is hardly any lab that basically does not have a Raman spectral measurement system. In fact, it was one of our aims that very soon we should be having a tabletop Raman spectrometer, which could be one of the experiments that you could do in your labs. 2-level lab or maybe a 3-level lab. The point is, it's become that easy to get Raman spectra done today because we have lasers. But what has happened is, it has not just given us a powerful light source to do Raman spectra better. The fact we have powerful light sources has actually opened up new areas of Raman spectra which we didn't even think about when we didn't have these light sources. And that is the realm of non-linear Raman and many other problems. Let's look at a situation where I have two levels. And let's say this is 100 wave numbers, or let's say 500 wave numbers. It could be some vibration, 500 wave numbers apart. So this could be V equal to 0, and this could be V equal to 1. 500 wave numbers apart, maybe a bending vibration of some sort. If I come in with a laser with mu1, what does the laser do? It will take me up there, and then I drop back, which is mu2, and mu1 minus mu2 is going to be 500. That's the round. If I have a laser, the experiment becomes good because I'm going to have a strongly scattering mu2 frequency. I can detect it even better. If I have even more juice in my laser, even more power in my laser, something new happens. And what is that? mu1, mu2, mu1 again, the molecule picks up second photon of mu1, and then what do I get? A big light that is scattered off, big large photon that is scattered off, and what is the frequency of that photon going to be? Is it going to be greater than mu1 or less than mu1? It has to be greater. It is almost like the first part of the experiment is transferring population from here to here, and the second part of the experiment is doing an anti-source. If I didn't do anything, my anti-source would depend on the population that is created in V equal to 1 by thermal process. At 500 wave numbers, what is my population going to be? KT is 200, therefore it's about 2.5, e power minus 2.5. So it's going to be roughly around 8% of the output. Not great. And given the fact that Raman is not a very efficient process, I'm going to have a tough time looking at the signal in terms of the anti-source lines from here. But what has this experiment actually done? In a way, what it has done is transfer population from here to here by this process, and then the second experiment actually is doing an anti-Stokes on this. You can model it that way, but what really happens is the whole thing is coherent. The whole thing is simultaneous. This, and then battery. The whole process occurs as if the molecule has interacted with two photons of mu1, one photon of mu2, and has given you this mu scattering which is coming out this way. So this mu s is going to be 2 mu1 minus mu2. And this process is a coherent process, meaning that if I have a sample and I shine mu1 into that, what I will also do is to shine mu2 into it. And what is mu2? mu2 is the frequency that actually brings me back to the state. In the normal Raman experiment, I shine this and I observe this. Now what do? I shine this and I shine this. So it essentially means that this process becomes accelerated. It's something like stimulated emission. It's something like the process is stimulated. So therefore I have mu1, I shine mu2, another mu1 is picked up, and what I get is mu f. I observe the scattered frequency. The way this experiment is done is the following. I shine mu1, I shine mu2, and what happens is from this a strong beam in one direction, that's why it's called coherent, is produced, and which is the scattered radiation that actually accounts for this little equation out here. This mu scattered will be equal to 2 mu1 minus mu2. And this process is called, it's a coherent process, therefore it's called coherent. And is it Stokes or anti-Stokes? Anti-Stokes. It's coherent, anti-Stokes, Raman spectroscopy. And it's acronym as CARS, coherent anti-Stokes Raman spectroscopy. It's anti-Stokes because the radiation that I'm really seeing is greater than the frequency of the incident radiation. Therefore, it is anti-Stokes. It's actually being produced by two laser beams that I'm putting inside in a coherent way. Therefore, it's a coherent process. And therefore, it's coherent anti-Stokes Raman spectroscopy, extremely sensitive, much more sensitive than the normal Raman spectra, even when done with lasers. And that's the reason why this is actually caught on. And today you will find that in most experiments where you need the sensitivity and you need some specificity in the way you're looking at processes, CARS or coherent anti-Stokes Raman spectra is actually extremely useful. Let me, before we leave this, let me look at another process. Let's say this non-electronic state A is a non-electronic state that we call it as X. And if I want to do Raman spectra by going from, let us say, here to here, don't worry about why I put the state so far. When I take this frequency and I go up all the way, where am I going to? A virtual state. And where am I coming back from? A virtual state. I land up here. And what is the scattered frequency going to be? It's going to be mu s by incidence of mu I, and mu I minus mu s must be this difference. And that's what I do when I do normal Raman spectra. I can keep changing this frequency because for Raman spectra, I don't need a frequency that matches any state. Because I'm just going to a virtual state. That's the reason why I could do the experiment with 300, 400, 600, 700 nanometers. As long as the frequency is more than the state separation, I get my experiment done. So the probabilities of cross sections are different. Longer the wavelength, over the cross section. But longer the wavelength, I suppress fluorescence. That's the reason why we're doing this. But now I can do something else. I keep changing this. Supposing I get up here, experiment would still work. This is a virtual state, and I come back here, and I still mu s, mu I minus mu s will be this difference. I keep varying this frequency. The scattered radiation frequency will vary, but in such a way that the difference is still going to be this. We know that. But when I get very close to the state, I won't touch the state. Because the moment I touch the state, what will happen? Or an absorption experiment. And once I have absorption, I have fluorescence. And then I am killed. So I won't touch the state. But I get very close to it. And what do you think will happen when I get very close to it? I'm actually not working out of a virtual state. I'm actually working out of a state that is very close to a real state. And suddenly you find that the cross section for Raman spectrum actually increases enormously. So I will keep varying this intensity and I keep getting it closer and closer to a real state, which could be this. Suddenly the scattered radiation intensity increases, and this process is called a resonance Raman spectra. So which means I am using an incident radiation, not just anything, but I am using it in such a way that it actually turns out to be a frequency that gets it very close to a real state, but not at the real state. Because the moment I hit the real state, then I am getting the new complications. I will have an absorption, I will have fluorescence and all these processes. So as long as I am very close to it, I don't cause an absorption. I am still doing virtual state spectroscopy. But that state being so close to a real state, suddenly the cross section, the probability increases, and you will find that resonance Raman actually is an extremely powerful process. Because it gives you a lot of intensity that you would normally not get with a normal Raman spectrum. That's one way to increase your Raman intensity. What's the second way? The second way is use new angles, both. And therefore you will find that what you're essentially doing is you're pumping it and you're forcing the molecule to come back, something like a stimulated emission, which you probably have seen in the case of lasers. And therefore if I have two laser beams, the probability for Raman emission actually increases quite a bit. And that's exactly what we're doing here. I use this to get up there. I use this to push the molecule back down here. So this is more like a forced or a stimulated emission out here. And the third beam actually takes me up and gives me the spectra. So how is this experiment really going to be done? I'm going to keep mu1 constant. I will vary mu2 slowly. And every time mu1 minus mu2 hits an energy difference, what do you think will happen? Oh, there is going to be a huge cross section or a huge probability for this process to occur. And therefore, if I actually plot the spectrum in which I keep mu1 constant, but I simply keep varying mu2, every time this mu1 minus mu2 turns out to be an energy difference between two states, I suddenly have a huge Raman line. Therefore, if there were many lines, many states out here, and I keep varying this would give me a huge intensity, this would give me a huge intensity, this frequency would give me a huge intensity, and this would give me a plurality. You will therefore see that I can simply tune mu2 such a way that mu1 minus mu2 actually happens to be the energy difference between two states. And every time the resonance is hit, I'm going to get a huge intensity as far as my Raman scattering is concerned. And therefore, the point we are trying to make is that once lasers came, you are not restricted to doing this normal Raman spectroscopy with more powerful light sources. No. All you are trying to do is that you are trying to drive Raman spectroscopy out of the normal realms and into realms where many photons are actually taking part in the whole process. You will have many photon participation in this whole process, such as here, 1, 2, and 3. And of course, if you put the fourth photon, which is a scattered photon, if you take that into account, you're actually looking at a 4-wave or a 4-photon issue. In this case, if you have this and this, it's a 2-photon issue. And therefore, you found that with the intensity that you can get out of the laser, with the fact that you can hit resonances, with the fact that you can actually tune them to differences, and because the laser intensity was so large, you are not stopping right here, you're actually coming out here and pushing it out again and getting it back. You found that you're actually running this experiment into a realm of nonlinear process. It is not just a one photon process. You are using many photons for the whole process. And this actually made the whole spectroscopy of Raman extremely powerful. Of course, there's another variation in which, in this case, what is between mu1 and mu2, mu1 was absorbed twice and mu2 was absorbed once. I can also have a situation in which mu2 is absorbed twice and mu1 is absorbed once, in which case, of course, I would get Stokes lines, not anti-Stokes lines. You can work that out. And in which case, of course, I'm going to have coherent Stokes-Raman spectroscopy, which is acronymed as, actually called scissors, with CSRs. So you have Stokes, coherent Stokes-Raman spectra, a coherent anti-Stokes-Raman spectra, you have a resonance Raman spectra, of course you have a normal Raman spectra than lasers. There are many more. There's a hyper-Raman and so on and so forth. We will not get into all the other possibilities that there are. All I wanted to do in the last 20 minutes or so that I've been talking to you about is to expose you to the fact that once lasers came in, you actually stepped Raman spectroscopy out of the realms of normal Raman and you got into the realms of nonlinear Raman. It also turns out that if I have a surface, I put a molecule on the surface, what do you think the surface will do to the polarizability of the molecule? It can actually increase it, because the surface will actually drag the electrons towards it, and therefore the polarizability of the molecule can actually be different, can actually be larger when the molecule is put on the surface. So as opposed to a molecule in the gas phase, a molecule on the surface can actually show you a Raman spectra that is orders of magnitude more intense. And you can do that. You can actually take silver particles, have your molecule absorb onto the silver particles, and then do Raman spectra on this combination. And you will find that the Raman spectra is enormously more intense than what you got otherwise. And this is another technique, it's called surface enhanced Raman, SERS. As I said, this is only to throw at you all the possibilities that exist simply because Raman spectra had this new tool that came into being in 61, which is a laser. As I said, these are not for the exam. These are only to let you know that these are all the possibilities. And if you're really interested, to look up and quite a large number of books that you will have in advanced spectroscopy that will talk to you about all these non-linear Raman. As far as this course is concerned, all I would like you to do is to be able to calculate the frequencies of various lines given the incident radiation and the energy levels of these molecules. You must be able to tell me what sort of molecules will show Raman spectra, what sort of vibrations will show Raman spectra, what the selection rules are, what sort of information one could get from looking at infrared Raman together. So we spoke about the principle of mutual exclusion, and all these are things that I would like you to keep in mind when we work on this. I think we'll stop here. What I will therefore do for those who came late, Friday's class will be at 4 o'clock. It will be from 4 to 5, because we have a lecture at 5 of that day. And that day we will look at the problems that I have sent you.